Good night, everyone. And this is a pre-record presentations. My name is Rian Fatah Muhammad. Thank you very much. It's been an honor to be able to present our research entitled Probabilistic Multi-Stability Assessment in Power Systems with Uncertain Wind Generations in this PMAPS conference. This paper is co-written with my colleagues Robin Brice and Ali Ehsan. In terms of paper indexing in PMAPS conference, this paper is the paper number 94. So let's start the presentations then. So this is the overview of the presentations. It starts with intro, which consists of reasoning and also research questions, followed with simulation setup and test cases. The result and discussion section is divided into three subsections. The first subsection is the result of individual stability types. Second one is impacts of levels of uncertainty on multi-stability area. The third one is impact of levels of uncertainty on relationship between stability types, and is with a conclusion. So as we know, global wind is increasing, and as a matter of fact, it has 6% of world electricity capacity by 2019, rising 10% from 2018. This has several implications. One of them is fluctuating system inertia. Of course, this is due to wind's variability, which leads to several power system issues. With the prominent example of this issue is Australian blackout due to renewable energy in 2016. This then leads me to ask, uh, what is the impact of varying wind generations on multiple stability types? And second, is there any impact of varying wind generations on the interactions between stability types? And if yes, to what extent? So these two research questions will be detailed in the next slide. And also, what can be taken from this research? So the first one, like the first research questions, several literature tends to assess wind generation's impact only on specific stability types, whereas in practical conditions, all stability types are interacting. Second one, as far as my understanding goes, is practical system, it is common to assume a system with satisfactory small signal response will have good large signal stability response as well. But will the additions of wind generation and other source of uncertainties alter these interactions? But if yes, to what extent? What about other interactions from other stability types? These two research questions will be answered by this research. So, in order to answer these research questions, I need to set up my research. So this is the simulation setup. First, I choose two area system as the test case. Two area system is a well-known for power system stability studies. However, I introduced two test cases with respect to two area system. The first one is low uncertainty. I define low uncertainty as in only load 1 and load 2 of two area systems being modeled as uncertain source. So as illustrated in this picture, load 1 and load 2 both are being modeled with respect to nominal loading curve, and on top of the variations result from loading curves, I add additional normal distributions on top of that value. Therefore, it has this kind of shape. The second test case is high uncertainty case, or in simpler way is when I add wind generations. The wind generations follows variable distributions of wind speed and is transformed using wind speed to power output, and is illustrated in this picture. I want to add as well that wind turbine employs type 4 VECC model, while VSCSV DC model is taken directly from Power Factory library. Both the impact of load and wind generations uncertainty is modeled to alter synchronous generator capacity under continuous derating. This derating will be detailed in the next slide. So I spoke about interactions of stability of small signal and large signals. However, other interaction between stability types also covered in this research. In total, 6 interaction of stability types will be considered, stemming from 4 stability types. So for each stability type is going to be measured using a common physical stability indicator, as shown in here. For small signal rotor angle, I use model damping factor. Large signal rotor angle, I use transient stability index. For voltage and frequency, I use system stability index and ROCOF, or rate of change of frequency as well. The details of this physical stability indicator is elaborated further in our paper. So this is to provide an overview over the continuous T rating. So these T ratings is a functions of active power generation, uh, cost V, and also capacity of each number of generation. As can be seen in this picture, with respect to other T rating types, discrete T rating, this is the illustration of continuous derating. It has a linear slope on it. And also, I employ stopping criterion to know how many Monte Carlo simulations is required for each stability types. As can be seen in this picture, for each stability types, the result of thousand Monte Carlo simulation has a satisfactory performance. Therefore, I choose a 10,000 Monte Carlo simulations for each stability assessment. So let's move on to the result and discussion. So first subsection is going to elaborate the impact of the same uncertainty source to different stability types. So sorry, I forgot to mention that all stability types are being assessed using the same data set. So same operating condition, same nominal values of loading of load 1 and load 2, same loading of same generations value of wind generators is going to assess under 4 stability types. So the first stability types that we are going to explore is small signal stability response. This is a plot of critical modal damping modes, critical modes, and it's a frequency of oscillation. This is with respect to no renewable energy. It has a very nice slope and pattern, but when the wind generation is at, and I want to mention that the high uncertainty has wind uh, generators in here, in which the wind generator is altering system's inertia. As you can see in here, the part of the broadly linear part in here is transforming into uh, so more and more uh, critical mode is being shifted into a more right side of imaginary plane. This result in as can be seen in the distribution function of this critical modal damping factor shown in this plot. Small signal stability response from high uncertainty case is worse than low uncertainty. So the same approach is then taken into account for large signal stability response. Is measured using transient stability index, which measure the largest displacement of any two rotor angle. The largest rotor angle of each 1,000 simulation is portrayed in here for both low uncertainty and high uncertainty. So this is the picture of distributions from the process rotor angle into transient stability index. It shows that large signal stability response from high uncertainty case is better than low uncertainty case, as less power is flowing through faulted line. The next stability assessment is voltage stability. It is measured using system stability index. It So same approach then taken into account. I convert this physical stability response into its SLI distribution function. It shows that wind generation causes higher SLI than at low uncertainty case. The last individual stability assessment is frequency stability. It is measured using rate of change of frequency. I think this is quite straightforward. because less system inertia is available to increasing wind generations, we can expect that the rock-off from high uncertainty is higher, or in other words, frequency stability response from high uncertainty is worse than low uncertainty. However, this type of individual stability assessment, like I said in the beginning, is quite well known. Several researchers already done that before. However, the value of this paper is to incorporate hi- uh, a study that encompassing all types of stability under a same uncertainty source. Therefore, um, in order to visualize this in an easier way to understand, I merge all of those four stability results into one parallel plot. So this is how I do the parallel stability plot. For each percentile, so I divide the partition this value, this distribution function into its respective percentiles. So for minimum, it shows in here, for low uncertainty case, it has a value of 0.43%. So with respect to the MDF axis, it starts with 0% and 1%. Therefore, if we have 0.43%, it should be located somewhere near here after 0.4%. Same is conducted with 5% percentile at 0.46, 25th, 50th, 75th, 95th, it should be showing 95th percentile. Is a typo, and end up with maximum. So we have plot, the area plots is the same plot of MDFs in here, and in here is the same with respect to the number of percentile that it shows. So the same approach then taken for transient stability index. It has an axis starting from 60 and ending at 90. However, I need to say that TSI has a value of 0 till 100, with a value closer to 100 showing systems that is more stable, and value closer to 0 showing a system that in the verge of instability. So we have at minimum value, a minimum value of 62.1 is located in here for low uncertainty case, and it's end up at maximum value of 82.5 somewhere in here. Same approach, then incorporate for voltage stability or system loadability index in here, and this is for rock-off. So what we are looking in here is a parallel plot of multiple stability types at low uncertainty with respect to its percentile shown. Well, I'm going to say that this plot is the same like these four plots, but it's quite easier. This is the plot at low uncertainty case, and I did the same for high uncertainty case. This is the picture, this is the plot of parallel of the high uncertainty. So what can be taken into account with respect to interactions between stability types? The first one is that a significant change on relationship between small signal rotor angle to others are visible, especially between set value of 25th percentile to 50th percentile. As can be seen in here, this is the area of 25th to 50th percentile. Whereas in high uncertainty case, it shows the area is changed dramatically from here to here. Another thing that's worth to mention is that in general, area under low and high uncertainty exhibit different shapes. And last, uncertainty source affect different stability types in a different way. Therefore, if we only take into account individual stability assessment, there will be a risk of under or over estimates of system stability. However, within the third section, and this is a picture of an area. However, I want to observe what's the impact of specific operating conditions affect different types of stability. This will be detailed in the next subsections. So as in here, we talk about the area, but in the next slide, we are talking about specific operating conditions. I spoke previously that for each stability types, the simulation is being run 1,000 times. Therefore, I plot a bottom 50th and top 95th percentile. Therefore, bottom 50 from 1,000 means that it is a plot of 50 operating conditions, and the red one showing top 95th percentile is the plot of 50 operating condition, resulting in higher than 95% of the result from the MTF. So for each operating conditions that result in bottom fifth of MTF, I I, I observe the value of other stability types. For example, in here, uh, worst case of MTF generally shows worst case of DSI as well and SLI. However, is the in and it match a general assumption that if you have good small signal stability response, chances are you are having a good large disturbance stability response as well. However, does this statement holds true in high uncertainty case? It isn't. And as a matter of fact, uh, once the level of uncertainty increases, the same pattern can no longer be assumed, or in other way, the interaction change. Or there is also an interesting fact in which certain operating conditions resulting in low value of MTF, portrayed with a box in here. A certain operating condition with result in low value of MTF, bottom fifth percentile, could yield to two cluster values of low and high value of DSI and SLI. However, due to time limitations, I'm not going to explore it in detail in here, but I'm saying that this is explored in detail in the paper. So you are very invited to read the paper. I want to revisit my intro. So what can be taken? I spoke in the beginning. What can be taken from this research? So one, I said that we can get information about the impact of varying wind generations on multiple stability types. And second one, knowledge on whether varying wind generations alter the interaction between stability types. And as a matter of fact, we did learn that in general, poor values of MTF generally correspond to poor values of DSI and SLIs in low uncertainty case. However, once the level of uncertainty increases, the same pattern can no longer be assumed. In other words, the interaction changes. Therefore, the importance of conducting a multi-stability assessment is justified as one, same uncertainty affects different stability types under varying effect, and the relationship between stability type is not necessarily straightforward. So that's the end of the presentation. Before I finish my presentation, I just want to mention the reference that I put within the presentations. The reference, source of image, label, and also contact persons. So thank you very much, and I just want to repeat what I just said in the beginning. It's been an honor to be able to present our research in PMAPS paper. So thank you very much, and I'm looking for all of your feedbacks. See you. Stop sharing and the meeting.